Welcome back to BAS 120. We're on Chapter 7. We're going to go through example 7.7, a two-tail test. So in the last example, we showed a one-tail. It happened to be a left tail. Now we're trying to do an example where we're going to talk about the average age. So the average age was 35 in this example. They took a sample of 34. There are the steps again, both for the critical value and the p-value. Step 1, our null hypothesis is our mean is equal to an age of 35. Notice this is a two-tail. We're just interested if the population is different than 35. So our alternative hypothesis is the population is not at an age of 35. Again, we assumed our alpha to be 0.05. That means our confidence coefficient is 1 minus alpha, or 0.95. Step 3 is to compute our test statistics. So we have our sample mean. We took a sample of, 34 people, and we got an average age of 38.6. Population mean or hypothesized mean for the null hypothesis was 35. There's our equation again for our test statistic. Our numerator, we calculated our sample standard deviation because our sigma was not known. There's our sample size. There's our t-distribution denominator. Our numerator, of course, is the difference between the two. There's our numerator. There's our denominator. There's our t-score. So this is 2.7 standard deviations to the right of our mean. So now we have to determine if that's far enough away from the mean. So came down here, took a two-sided test. We use a slightly different TINV 2T, and that gave us a t-distribution critical value of 2.035. We went ahead and did our p-value. So it's left to right, so we did 1 minus our function, our norm S disk for our sample. We got a t-score of 2.7, a critical value of 2.8. So again, we're to the right, we're higher than that, so we're in this rejection region. So we're going to reject the null hypothesis. Our p-value of 0.003 indicates that there's only a 0.3% chance that we would get that score or greater, which is well less than our alpha. So the probability of getting these results is extremely small and in our rejection region. So when step 5, we compare the two statistics, we will, our test score is in the rejection region compared to the critical value, and our p-value is extremely low, so we'll reject the null hypothesis. So we'll conclude that it is so unlikely that we would get these results that we can conclude that the average age is not 35. And there's all the raw data, and there's where we calculated the mean in the average. So that's a two-tailed t-test. So we've done a one-tailed t-test, a two-tailed t-test. If it was a z-test, it would just be a different, same steps, just a different test statistic. You would use the z-score. Those are rare instances because very, very rarely is sigma, the standard deviation of the population, known. Let's do example 7.8 because we've done it for a one sample for numerical data. What about a one sample where we have a proportion? Now remember, a proportion is where our results are yes, no, pass, fail. So in this example, it's customer satisfaction. The customer satisfaction level, as equated by them scoring a certain level, was 75% of the customers rated themselves as satisfied. The sample size, we took a sample of 44 after improvements. We want to know if those changes have improved customer satisfaction. So lots of things we could have, this is lots of applications in business. We might have added staff. We might have changed the decor of the building. We might have added additional services. We want to understand if customer satisfaction levels is up significantly. Now, down at the bottom, they gave us the raw data for CADsoft. We had to do a little bit of manipulating because notice it was 1 through 5, and they told us that they rated people as satisfied if they scored a 3 or a 4. Okay, so we went in here and we did our COUNTIF function. We said go through all of this and count if it's greater than 2, i.e. a 3 or a 4. We then went down here and just calculated a proportion. 35 people rated a 3 or a 4 out of 44. That is a proportion of 0.795. So, good news, customer satisfaction was 75% before the improvements. Now it's very, very close to 80%. But we have to go through the test to see if that's significant enough for us to be able to claim that these improvements have improved customer satisfaction. So step 1 is the null hypothesis is customer satisfaction is less than or equal to 0.75. Understand, we're doing a proportion now, and it's a one tail. We're only interested in the right side. We're not interested if customer satisfaction went down. We're trying to prove that we're not trying to prove that customer satisfaction changed. We're trying to prove that customer satisfaction improved. So we're only interested in the one tail, the right tail. Step 2, we have to assume how confident do we want to be? Well, we want to be, how sure do we want to be? We're going to use an alpha of 0.05. So a confidence coefficient of 1 minus the alpha, 0.95. All right, slightly different test statistic for a proportion. It's p hat minus what our population proportion is, divided by the square root of the population proportion times 1 minus the population proportion, all divided by n. So we got our sample proportion. We mentioned we went ahead and calculated that. We had to do a little manipulation, right? Because we had to do a count if it's 3 or 4, which is oftentimes what you're going to have to do with raw data. You're going to have to do some manipulation to get it before you can do your hypothesis testing. But we got a p hat or a sample proportion of about 80%. Our population proportion or our assumed population proportion, what we assumed for our null hypothesis was 0.75. So we calculated the numerator, we calculated the denominator, we got a z-score of 0.696. So that's 0.696 standard deviations because it's a positive number to the right of the mean. So we're to the right of the mean. It's a one-tail test. We use this to find our critical z-value, norm.s.inv. Our p-value, notice we do 1 minus this because we're at the right side. There's about a 0.24 p-value or a 0.24 probability that we would get that test statistic or higher. So right off the bat, we can kind of conclude before we even get to step 5 that if our test stat is 0.69 and our critical value is 1.6, we are not in the rejection region. Or if we look at the p-value, 24% probability or 0.24 is not even close to our alpha of 0.025, the level that we want to be sure. So we have not, even though we've gotten results that show improvement, they're not that unusual or they're not that unlikely for us to be allowed to reject our null hypothesis, which is right down here. We did not fall within this rejection region. Notice the critical value is 1.65. We're not even close to that. We're in here. We need to be somewhere out here to reject it. Same thing for the p-value. We want this to be only a 5% chance probability that we get this score. Well, there's a 24% chance that we would get close to an 80% score or higher. So we do not reject the null hypothesis. Now, just like the other examples we've gone through, you do have evidence that customer satisfaction's improved, so you'd probably want to do some additional testing, additional sampling, because again, just like the legal analogy, gee, we have evidence this guy's guilty, but I don't think we have enough evidence to prove it in court. So what a lot of folks would do is keep digging for additional evidence, and that's probably what you would do here because the customer satisfaction did jump from 75% close to 80%. So you'd probably want to do some additional sampling. But based on the data you have to date, the 44 sample you took, you cannot conclude that customer satisfaction has improved significantly. Any questions, let me know. So we've gone through a one sample, two tail for the t-test, and we've gone through a one sample for a proportion.